Hello everyone. In last lecture I was discussing modified Goodman diagram for fluctuating types of bending stresses as well as axial stresses related topics. There I discussed about modified Goodman diagram for bending stresses case, especially in fluctuating types of bending stresses case. Apart from this thing, I was discussing about a problem which is related to finite life problem for fluctuating types of bending stresses cases. Now, in today's lecture, first of all I will discuss about another one example. I will solve that example, and that problem is based on fatigue life estimation which is subjected to fluctuating types of bending stresses, and it is for infinite life problem. So, this is the content of today's lecture. First of all, I will discuss about a problem on infinite life fluctuating types of bending stresses problem. After that, I will discuss about modified Goodman diagram for torsional shear stresses cases, and after that actually I will solve one problem on fluctuating types of torsional shear stresses cases using modified Goodman diagram of fluctuating types of torsional shear stresses. So, first of all this problem which I will solve, this problem is for infinite life problem which is for fluctuating types of bending stresses case or bending loading case. So, here the problem statement is like you can see from here the problem statement, a cantilever beam. Now, all of you are very well familiar, beam means which is subjected to bending moment, or you can say transverse types of load about its axis. You can see fluctuating types of bending stress case. The problem statement is like a cantilever beam. All of you are very well familiar what is cantilever beam. Cantilever beam means one end fixed and other end free, and other end there is it is subjected to a transverse types of point load, you can see here. So, a cantilever beam made of cold drawn steel, this is the steel specification. The steel has a ultimate stress. So, here first of all what are the things given, that I will just note it down. So, ultimate strength is given as 600 MPa, you can see. Yield strength is given as 380 MPa, you can see. Okay. The force, this at the free end P, you can see acting at the free end and varies from minus 50 to plus 150. So, this P load varying from, you can see, minus 50 Newton to plus 150 Newton, you can see. The expected reliability is considered as 90%, you can see. So, based on this we will use marine different constant, that is reliability constant. We will see what is the reliability. Then here the factor of safety is given as, Fs is given as 2. The notch sensitivity factor, so here Q is also given as notch sensitivity factor given as 0.9. What we need to do? We need to determine the diameter d for infinite life of this problem. Okay. So, what should be the diameter d, you can say, that we need to find out which is not fail due to these types of loading case, that means for it can sustain infinite number of cycle, that we need to find out. So, for finding out these things, first of all we need to find out what? First of all we need to find out the endurance limit for this cantilever beam. So, endurance strength for this cantilever beam, endurance limit for this cantilever beam we need to find out, that we can find out by marine equation. You know this thing, marine equation. So, what is endurance strength for using marine equation, that you know, that is equal to K, Kb, Kc, Kd, Ke, Kg and 0.5, as it is a steel material, that is why 0.5 into S ultimate strength, that is very well known to you. Now, here Ka is given as, for these types of ultimate strength, this K, and as it is a cold drawn types of steel, that is why Ka is given as, this K is given as 0.77, that we can find out from the chart. So, directly I am putting, actually instead of using chart I am directly putting the thing. So, let us consider here the diameter of this, let us consider the diameter which is varying in between 7.5 to 50 millimeter. Let us consider this, I am considering. Okay. So, for this range of diameter we know this Kb value, that is size factor, generally this Kb value is so first Ka equal to 0.77, Kb is for if it is varying from 7.5 millimeter to 50 millimeter, its value Kb value is, you know, that 0.85, it is very well known to you. Now, reliability factor Kc, for 90% reliability, that also we know. For 90% reliability, generally this Kc value is 0.897 from the table which I have discussed earlier lecture. From there you can get this data. Okay. And Kd is modifying factor due to temperature. So, that is neglected here. So, that value will be 1, and Ke, Ke is generally you can say the stress concentration factor, here we can consider, as here there is a fillet, here you see there is a fillet. So, there is a fillet means there is a abrupt change. So, generally this fillet radius ratio as well as this capital D by a small d ratio, generally there is chart available. From that chart we can easily find out what is the theoretical stress concentration factor. So, here based on the chart, so I am not directly showing the chart, you can get the chart from some standard book itself, it is available. So, I am just directly showing how to find out this thing. So, here generally this fillet position, this curvature radius r by fillet position, the smaller diameter of this cantilever beam is, this ratio is given as 0.2, you know, because you see from here you can, and also this capital D by a small d, this diameter ratio, capital D means this is capital D, this is a small d. So, this d by d ratio for this fillet types of cantilever beam, it is 1.5. So, for this ratio generally there is a chart available. From that chart we can easily find out what is theoretical stress concentration factor Kt. So, this theoretical stress concentration factor based on this generally ratio of smaller by capital D and capital D by a small d ratio, this value is generally Kt value is 1.44. This we can get from some standard chart available, some standard rule book it is available, you can get this data. So, theoretical stress concentration factor Kt equal to 1.44. Now, if Kt is given, now we can easily find out what is actual stress concentration factor or fatigue stress concentration. So, Kf we know as 1 point Notch sensitivity factor into Kt minus 1. This is very well known to us. So, based on this equation generally we can easily find out 1 plus Q Notch sensitivity factor is given as 0.9, you can see from in this problem it is itself given, and Kt from the chart we find out, and minus 1 is given. So, by this generally we can get Kf equal to 1.396. Okay. Now, if Kf is given, so we can easily find out what is Ke. So, Ke we know this 1 by Kf. So, K equal to 1 by Kf, this is giving us a value which is 0.716, 0.716. Okay. So, here I am writing K is equal to 0.716, okay, and Kg, as it is a bending types of loading. So, here Kg is generally 1 and there is 0.5 and ultimate strength is given as 600 Newton per millimeter square or MPa, you can say. So, this will give us a value of what it is called endurance strength equal to 126.11, 126.11 MPa. So, MPa means you know it is Newton per millimeter square, because 1 MPa equal to 1 Newton per millimeter square. Now, second case, what are the things we need to do? We need to draw the modified Goodman diagram. So, second, this is a step 1, you can say this is a step 1, second step, step 2 you can say. So, in this step 2 we will construct modified Goodman diagram, construct modified Goodman diagram. So, step by step I am just solving the problem, so that I will not skip a single step here, so that it will be easy to solve problem in future. Actually, this is a generalized problem I am solving. For this case, if you consider welding case, for that welding related stress concentration factor is come into picture, there generally welding effects will come. Based on this thing you need to design the structural component. So, here that is why this generalized problem I am solving. So, if steps you will be aware, then what happens, rest of the things you can do very easily. For constructing modified Goodman diagram, first of all we know ultimate strength value, we know what it is called endurance strength value. So, we can easily, and yield strength value is also known to us. So, we can easily construct this what it is called modified Goodman diagram. How modified Goodman diagram required to draw, that I am just showing, directly I am showing here. So, this axis represent generally mean stress, this axis represent amplitude of that stress. So, for modified Goodman diagram we know endurance strength and this is your ultimate strength. So, by this we need to draw a line, this is the Goodman line, you can say this is Goodman line, Goodman line. This we need to modify with the help of yield line. So, that is why yield line I am going to draw. Okay. So, this for yield line, so both the axis I need to take yield strength value, this yield strength value. So, after that this yield strength, this 2 point I need to join, this is called yield line. So, let us consider this is our A, this intersection point is B, this point is let us consider this is our C, this is our D point. Okay. So, here this modified Goodman diagram portion is, we know this modified Goodman diagram is O, A, B, C. This is the portion which is the shape portion, you see, you know these things. I have already explained these things clearly. Now, what are the other things required to do in this modified diagram for infinite life problem? We need to draw the load line. So, load line how to draw, I have already explained during the explanation of what it is called modified Goodman diagram case. For that, generally what are the things we need to find out? We need to find out first maximum bending stress. So, here what is the maximum bending stress? Maximum bending stress will be your P max into L, you can say. So, here P max is given as 150, okay, plus 150 is given. So, 150 Newton, and L generally we need to find out L, because we need to find out the small diameter. So, that is why here we need to take the L from this flat position to end of this position. So, this is our L. L is equal to 100 mm. This 100 mm I am considering. Okay. So, that is why here L is 100 mm. Okay. 100 once you consider, this will give us 150,000. Okay. This Newton millimeter. This is the bending moment, maximum bending. What is minimum bending moment? So, minimum bending moment will be P min into L. Here P min is given as minus 50, L is given as 100. So, this is given a value of 5000 Newton millimeter, that you can see. So, maximum and minimum we calculated. Now, we need to find out what is the mean bending stress, mean bending moment, and what is amplitude of the bending moment. So, mean means you can say MB max plus MB mean, you know these things, divided by 2. So, based on these things we get a value of 5000 Newton millimeter, and amplitude is generally, you know, I have already discussed this thing clearly in previous lecture, MB max minus MB mean divided by 2. So, this will give us a value of Newton millimeter, Newton mm, correct. So, now we need to draw a load line. For drawing load line, we need to find out theta value, which is made by the load line with horizontal axis. So, theta value how we can find out? We know tan theta, I have already explained. For drawing load line, we need to find out tan theta is equal to MB amplitude divided by MB mean. So, this is giving us a value from this two value, you can see, that is MP amplitude is 10,000 and MB mean is 5,000. So, this is giving us a value 2. So, this will give us a theta value, which is actually, you can directly I am writing 63.435 degree. Okay. This you should keep it in mind. So, based on this theta value, we need to draw a, so I am drawing a load line OE. So, this load line OE, where this angle with horizontal or abscissa, horizontal axis, or you can say with abscissa, it makes a angle theta, which is 63.435 degree. So, this load line cut the modified Goodman diagram at a point. Let us consider this point is x. Okay. This x value, whatever the in x, whatever the what it is called S mean and S amplitude is there, this S m and S amplitude we need to find out. In this x point, what is mean stress value, what is amplitude value, that I need to find out. There are two unknown, one mean stress and one amplitude stress. So, for that actually this load line equation we know. So, what are the things? Another equation is required, correct. So, that equation we will use, that is actually Goodman equation or Goodman line. So, Goodman line, all of we are very well familiar what is Goodman line. So, here you can see, so Now, step 3, here we will find out what is Sm and what is amplitude value. These are the things we need to find out. So, for finding out these things, here we need to use two equations. One equation is actually Goodman line equation, we know Goodman line, that is here you can say AV line equation, we can easily find out. So, AV line is SA by S endurance strength plus you can say Sm divided by S ultimate strength, this is equal to 1 without considering the factor of safety here. Factor of safety during permissible stress calculation purpose, there I will use that factor of safety. Here also you can use, but what happens there I will use, then it will be very easy to understand. So, this is the Goodman line. So, in this Goodman line endurance strength, ultimate strength is given. So, what are the things we are getting? So, SA by endurance strength is I have calculated already 126.11 plus this mean stress value, ultimate strength is given as 600, this equal to 1. So, this is, let us consider equation number 1. Another equation is given, that equation is actually given as, you can see, what are the equation? Tan theta you can write as S m S A by S m, S A by S m. So, S A by S m is given as, this value is given already, tan theta value is tan 63.435 degree, this is given equal to your 2 is given. So, from this equation we know SA is equal to, we can write 2 into Sm. So, this is let equation number 2. So, by solving equation number 1 and equation number 2, what are the things we can find out? We can easily find out what is SA value. So, SA, so here I am writing solving, by solving equations 1 and 2, we can get mean stress value equal to, directly I am writing 57, that means at x, what is the value of mean stress, intersection point of Goodman line and load line, this much MPa and 114.12 MPa megapascal. So, we got this what it is called x point. So, what is the intersection point coordinate x? Sm comma SA, this will give us x is equal to, you can say 57.06 and this amplitude value is given as 114.12, correct. This is now clear to us. Now, we need to determine the diameter of the beam. So, step 4. So, step 4, here I will show you what is permissible you can say amplitude stress, or you can say this is called design stress also, you can say this permissible amplitude stress will be, you can say I am writing let sigma A, this sigma A should be your whatever the crossing point x amplitude you find out, that divided by factor of safety. So, here the factor of safety's application is coming. Okay. So, this will give us a value that is given as SA is given as 114.12 and factor of safety is given as 2. Okay. Now, here you see this sigma A, this is a bending stress. So, we know for bending stress case, we know the equation is, you can say m y by I. So, m y by I. So, here amplitude, this m equal to which m we need to consider, here m we need to consider as amplitude of that, whatever the amplitude of bending stress, that we need to consider. So, we already found that amplitude, that is 10,000 Newton millimeter. Here y is what? Y is a small diameter by 2, d by 2, and I, that is the second moment of area or moment of inertia, area moment of inertia, that you can say. For circular cross section, we know that is generally pi d to the power 4 by 64, that is very well known to us. So, equal to, you can write as 114.12 divided by 2. Okay. So, here from this equation we can easily find out what is d. D equal to, you can write as 12.13 millimeter. So, if the diameter of this, small diameter of this fillet types of shaft is 12.13 millimeter, then what happens? It will subjected to infinite life, that means it will not fail due to these types of fluctuating bending load. This you should keep it. So, this is the design diameter of that what it is called beam. So, this is the problem for infinite fatigue life problem, okay, which is subjected to fluctuating types of bending loading. Now, we will discuss about what it is called modified Goodman diagram for fluctuating types of torsional shear stress. So, for fluctuating types of torsional shear stress, generally we will discuss about what is modified Goodman diagram. So, for torsional types of shear stress, generally here we will draw the modified diagram. What are the steps generally we used to follow, that I am showing. So, here the horizontal axis or abscissa is represented as, you can say, torsional mean stress. So, here torsional mean, it is a shear stress. So, that is why here I am writing S M, okay. Stress, S represent shear, M represent mean, okay. And this vertical axis represent stress due to shear and its amplitude, that means torsional shear stress amplitude. So, here I am writing torsional shear mean stress and here I am writing torsional shear amplitude stress. So, if we draw the things, then what we used to get, it is observed that generally this torsional mean stress have not up to certain point, you can say torsional mean stress do not have any effect on what it is called endurance strength or torsional endurance strength, that you can say. So, that is why once you draw the failure point, you will observe that it is generally up to certain point, it is not that means your endurance strength is remain constant, it is not varying with this mean stress value. What I am telling, understand? This you should keep it in mind. So, that is why torsional endurance strength is not dependent on torsional mean shear stress. What I am telling, understand? That is why here you can draw if we draw a line considering this failure point, whatever the failure point you got, it is find out from experimental observation, and there is some theoretical interpretation also there. So, these are all called failure point. So, it is observed that this failure point for torsional types of fluctuating loading cases is not, you can say it is horizontal in nature. That means, with variation of mean shear stress, it is not changing, what I am telling, understand. So, up to certain point it is observed that it is not varying, that means you can say this. So, this is generally you can consider as endurance strength due to torsional shear. So, if we draw a line, then you will see this will represent a horizontal line. So, let us consider this line I am representing AB, which is a horizontal line, what I am telling, understand. At A position, as it is a horizontal line with respect to, you can say, abscissa, that is why you can consider the whatever the stress at A point you are getting, that is also called endurance strength due to torsional shear stress. So, you can say at A, whatever the stress you are getting, here I have shown that SE, this is called torsional endurance strength torsional endurance strength, this you should keep it in mind. And it is observed that up to certain point, generally this endurance strength is not varying due to variation of mean shear stress, this you should keep it in mind. Now, here also generally for modified Goodman diagram in case of torsional shear stress, here also we need to draw what, a yield line. This yield line will be the will consider the yield strength due to shear. So, here I am drawing on point in abscissa, that is the yield strength due to shear, that is why S y y t I am writing, yield strength due to shear. Okay. And if we draw a inclined line, if we draw a inclined line with respect to this yield strength due to shear, let us consider this makes a angle 45 degree, this you should keep it in mind. So, we cut this is called yield line due to shear yield stress, this you should keep it in mind. Okay. Now, this generally cut the diagram, this horizontal line at a point, let us consider B. So, what is modified Goodman diagram for fluctuating torsional shear stress case? So, here the modified Goodman diagram represent OA, B, and let us consider this C. So, here this OA, B, C, this region is called modified Goodman diagram due to fluctuating torsional shear stress, due to fluctuating torsional shear stress, this you should keep it in mind. So, here generally inside this OABC region, whatever the point will be, this is generally safe zone. Outside this modified Goodman diagram, this is generally failure zone, this you should keep it in mind. So, this is generally, here one things you can observe, very interesting things you can observe, that it is not necessary here to construct a fatigue diagram for fluctuating torsional shear stress, because here generally AB is, whatever the AB line is there, here you can see this AB line generally, which is you can observe that which is parallel to abscissa, correct. So, that is why here we need not to draw a what it is called fatigue diagram, like in bending case and axial case we draw fatigue diagram like modified Goodman diagram, then Soderberg diagram, different diagram we use, but here we need not to draw a fatigue diagram. So, here one things you should keep it in mind. So, here fatigue failure will be indicated if the you can say shear stress amplitude is equal to, you can say is equal to endurance strength due to shear. Then if it is crossing this boundary, then what happens, you can say it is subjected to fatigue failure. For a static case generally if it's crossed this yield line, whatever the yield line value is there, if it is crossed this yield line stress amplitude, then what happens, you can say it is subjected to a static types of failure.